Hello, my name is Samuel Palmer. I'm going to be giving a presentation on Greek geometry and the problems of antiquity. This is for my pro seminar in math. My advisor is Dr. Donald McGinn, and I'm a student at the University of West Florida. So just a quick outline of my presentation. First, I'll just give an introduction, statement of the problem, talk about some background and relevance, and then give some selected constructions, ones that I think are relevant to the problem. And then we're going to shift gears, talk about algebra, some group theory and field theory, and finally we'll finish off with some satisfying proofs. So in Greek mathematics, they loved geometry, and they loved straight edge and compass constructions. These were basically constructions just using these two simple tools. The straight edge, which is like a ruler. You can use a straight edge to draw straight lines, but it's not marked, so you can't measure any distances, you can't do anything like that. And then we have the compass, which is a tool for drawing circles. You can just adjust the compass to whatever radius you want and draw the circle. So using just these two simple tools, the Greeks, they figured out how to construct all kinds of polygons and figures and results, but there were some certain things that they had trouble with, and these are the problems of antiquity. And the goal of this presentation is to prove that they are impossible. So what are these problems? The first is trisecting an arbitrary angle theta. So this just basically means if we have an angle, it is impossible to divide it into three equal parts. The second is constructing a square with the same area as a given circle. This is commonly known as squaring the circle. If you give me a circle, I can't give you a square with the same area using straight edge and compass. And finally, we have constructing a cube with double the volume of a given cube. If you give me a cube, I can't give you back a cube with double the volume using straight edge and compass. So before we understand why these are impossible, we want to talk about what is possible using the straight edge and compass construction. And I want to cite Euclid as pretty much the main source of all of these. He published his Elements around 2,000 years ago, and it has hundreds of results that he showed using straight edge and compass alone. It's really amazing how he starts with almost nothing, and he builds on it and builds on it until he has a whole plethora of knowledge. So if you like math, I would strongly suggest Elements. In Elements, Euclid lays out 5 postulates. These are basically just truths that are commonly understood to be true. Can't really prove them, but they're true. The first is that you can draw a straight line segment through any 2 points. Nothing new. If you give me 2 points, I can draw a line through them. The second is that you can extend any line segment indefinitely. So if we have a line segment, we can use our straight edge to extend it one way or the other way, both ways, however far we want. Given a line segment, we can also draw a circle with that segment as the radius and one of the endpoints as the center. This is Euclid's third postulate, and obviously we can do this with the compass. His fourth postulate is that all right angles are congruent. Nothing new here. 90 degrees is always 90 degrees. And his fifth postulate is kind of a famous one. It's a little bit complicated and wordy, but it's the parallel postulate. And it's really not necessary to proving our result, so I won't be going over it, but it is really interesting. And there are, in fact, geometries that do not use the fifth postulate, or they violate the fifth postulate, which is why they're called non-Euclidean geometries. So those are really cool also. So the first construction I want to talk about is the equilateral triangle. What Euclid wanted to do here was start with a segment, shown in blue, and he wanted to create an equilateral triangle using that segment. So what he did was he constructed 2 circles using the segment as the radius and the endpoints as the centers. And when he did this, the 2 circles intersect, and we have a third point, which happens to be the third point of our triangle. And this makes sense when you think about it, because all of these segments are radii of the same circle, so they must be equal, and thus the triangle must be equilateral. Next we have the duplication of a segment, and I should give some background info here first. So the way that the postulates are worded, we can't actually use the compass to transfer a distance somewhere else on the page. That is, we can't just trace over, say, the segment BC with our compass and transfer it somewhere else, like magically, and have that distance somewhere else. No, we're not allowed to do that. So Euclid comes up with this weird roundabout way of duplicating the segment CB at the point A. And he does this using a big circle. That big circle with the points E and F. You can see it has the radius DE and the radius DF, so these segments are obviously equal. We also have the equal segments DA and DB, since they lie on the same equilateral triangle. So we can say that DF minus DA is equal to DE minus DB. So AF is equal to BE, but BE is equal to BC because it's the radius of the same circle. So finally, we have that BC is equal to AF, which is what we desired. Next, we have a perpendicular bisector. This is a segment that cuts another segment in half, and it does it at a 90-degree angle. And the way you do it is you use the endpoints of your segment as the centers of two circles, and the radius of these circles just has to be greater than half of the length of your segment. It has to be the same for each circle, but it has to be greater than half the length of the segment. So when you do this, you get two circles, as you can see, that intersect. The whole circles aren't drawn, but you can still see them, and you can see the points of intersection. And when you connect these points of intersection, you obtain the perpendicular bisector. So next we have some operations using straight edge and compass, addition and subtraction. And these are really trivial. You can pretty much just use the compass to transfer alpha and beta to be adjoined. And remember, I said we're not allowed to do this, but now we actually are, because we've proven that we can transfer the distances using not using the compass. So now we're just going to do it for quality of life reasons. It's way easier just doing it with the compass than doing that whole lengthy transfer distance construction. So we transfer alpha to be adjoined to beta, and that's how we add. To subtract, all we have to do is adjoin alpha to beta, and then draw the circle with center at the endpoint of beta and radius alpha. And what that basically does is it cuts off alpha from beta. So the segment we have left on the outside of the circle is beta minus alpha. We can also multiply and divide using straight edge and compass. And how we do this is parallel lines and similar triangles. So I'm going to go ahead and tell you that these triangles in each figure are similar. So, for example, in the figure on the left, the smaller triangle is similar to the larger triangle. And this is because the lines are parallel. So we can say that 1 is to alpha as beta is to alpha beta. And when you actually write out these proportions, you get alpha times beta equals alpha beta, which is what we desired. Next, we have square roots using straight edge and compass. And how we do this is we create a circle with a diameter 1 plus alpha. So it has a radius 1 plus alpha over 2. And then we create a perpendicular to this segment at the point where 1 joins alpha. This is not a perpendicular bisector, just a perpendicular. So this segment, this perpendicular segment, it intersects the circle at the point square root alpha, or at the length, square root alpha. So it's really interesting. You can actually take square roots using nothing but straight edge and compass alone. So now we have all we need, and we're going to shift gears to algebra so that we can actually tackle these problems. And first we're going to define a group. A group is a set G with a binary operation star with these following properties. The first is closure. That is, if we take any two elements of G, A, and B, and do A star B, we get also an element of G. The second is associativity, which means that rearranging the way that we do the operations doesn't matter. This has to be true for all A, B, and C, and G. The third property of a group is an identity element. We call it E. So we have to have an identity element such that when we operate on any other element with the identity, we just get the element itself. So, for example, in a group like the integers under addition, our identity element is 0 because when we add 0 to any number, we get the number itself. And finally, we have inverses. For every element of G, we can find an inverse of A, such that A star A inverse is equal to A inverse star A, which is equal to the identity element. So in a group like integers under addition, we could have, say, 6, and its inverse would be -6, because when we do 6 plus -6, we get the identity element 0. And we also want to define an abelian group as a commutative group, which basically means that A star B is equal to B star A for every A and B in G. So something like the integers under addition would be commutative because the order doesn't matter. And we also want to define a ring. A ring is basically just a special kind of group, and it has two operations. We usually call them addition and multiplication. And it also has some conditions. So the set R along with addition have to form an abelian group or a commutative group. We also have to have associativity with multiplication. We also need distribution properties. You probably know these from regular integer addition and multiplication and real number addition and multiplication, but sometimes we can apply it to more broad sets. It doesn't always have to be numbers. So we need the left hand and the right hand distribution laws for a group to be a ring. And last, we want to define a field as a commutative ring. It has to contain an identity 1, multiplicative identity, and we also have to have that every non-zero element is invertible. So F is a field if F is a ring, and we have 1 in F, and we also have to have inverses for every element of F not equal to 0. We can also define a subfield as a field that is contained in another field, so a field that is a subset of another field. It also has to be a field under the same operations as the original field. That was a little bit of a mouthful. But we can also think of it as E being an extension field of F. So if F is a subset or subfield of E, then E is an extension field of F. It's just two ways of saying the same thing, really. And when we have an extension field, we can talk about the degree of an extension field, which is the dimension of a vector space. For example, the degree of the complex numbers with respect to the real numbers is 2, because we can't create the complex numbers with just a basis of one element of the real numbers. We need two elements in our basis. So we need basically an imaginary component here. So when we introduce I into our basis, we have 1 in I, so our degree is 2, because the dimension of our vector space is 2. Next, we have a really useful theorem about extension fields. It's basically if we have a tower of like 3 or more extension fields, we can state a certain fact. If K is an extension field of E is an extension field of F, then the degree of K with respect to F is just the degree of K with respect to E multiplied by the degree of E with respect to F. That asterisk is just standard multiplication, because the degrees are just going to be positive integers. And with those constructions that we have earlier, and now these theorems and algebra that we have now, we can now tackle the problems of antiquity. So we know for a fact that the constructible numbers form a field. This is because we can add them, subtract them, multiply, and divide them. You remember those pretty pictures I showed you in figures 3 and 4? It guarantees that the constructible numbers form a field. We also know that constructible numbers contain at least rationals. And this is also clear from our constructions, because if we create, say, 1, we can obviously add 1 to itself or subtract it and obtain the integers. And then we can just divide these integers by other integers using our division and obtain rationals. So we know that the constructible numbers at least contain the rationals for a fact. So we know that the constructible numbers have to be some extension then of the rational numbers, because we know also for a fact that we have irrational numbers. For example, the square root of 2, we've shown that we can construct that, but it's not in the rationals. And you can actually show algebraically that the only possible extension to f is square roots. Like I said, we know that square roots are an extension, but now we know that they're the only extension. And you can actually show this using some really ugly algebra. When you look at the equations of lines and circles in space, these are all equations in variables that are quadratic. So you have, say, an x squared, a y squared, and when you crunch the numbers, you pretty much always end up with something that is a square root, or a square root of a square root. So because of this really ugly algebra that I didn't include, we get this fun fact that the degree of q adjoined with some constructible number alpha is always a power of 2. An integral power of 2, I should say. So it could be 1, 2, 4, 8, 16, anything, but it must be a power of 2. And this is really the crux and the crucial point to proving why these problems are impossible. Just remember that the degree of an extension field of q with a constructible number must be 2 to the power r for r an integer. So the first claim we're going to tackle is the trisection of the angle. It is impossible, and we can now prove it to be impossible. Since we're trying to show that an arbitrary angle is not trisectable, we can actually just choose a specific one, and if we prove that one is impossible, then we've shown that an arbitrary angle is impossible. So we'll choose 60 degrees, and trisecting 60 degrees is equivalent to constructing a segment of length cosine of 20 degrees. So we'll call cosine of 20 degrees alpha. And what we end up with alpha is a cubic equation. We have 1/2 equals 4 alpha cubed minus 3 alpha. This is due to a trigonometric identity. And since alpha is the zero of a cubic equation, that means that the degree of q adjoined with alpha is 3. And 3 is not a power of 2. So the trisection of the angle, arbitrary angle, is impossible. But I should state that you can trisect specific angles. So for instance, 180 degrees, we actually trisected that earlier with the creation of the equilateral triangle that has 360 degree angles. You just can't trisect any arbitrary angle. For example, we've just shown that 60 degrees is impossible to trisect. Next, we're going to show that constructing a square with the same area as a circle is impossible. So we're going to assume that we have a circle with radius r. That means that the circle has a radius pi r squared, and so a square with the same area would have area pi r squared, and this leads us to the fact that the square has to have the side length r square root of pi. Now this is already a problem because pi is what's known as a transcendental number. So a transcendental number can't even be obtained by a finite number of algebraic operations. And because of this, we can't create it with a finite number of algebraic steps, and so it's not constructible. Pi is not constructible, so square root pi is not constructible, and this side length is also not constructible. So squaring the circle is also impossible. Last problem, constructing the cube with double the volume of a given cube using straight edge and compass. Now let's say we have a cube. Let's say its side length is x. The volume of that cube is x times x times x, or x cubed. So the cube that we want has a volume of 2x cubed. So if we do a little algebra and take the cube root of 2x cubed, we find that the cube that we want has a side length of x cube root of 2. Now the cube root of 2 is also the root of a third degree polynomial. So that's problematic once again, because the degree of q adjoined with cube root of 2 is 3, and 3 is not a power of 2, so it is impossible to double the cube. So in short, after pretty much 2,000 years, these ancient problems were finally proven to be impossible. And it's really interesting to me that these geometry problems, they get reduced to just algebra at the end of the day. I find it really fascinating, and I think that that same shift in perspective might be able to help us solve today's most difficult math problems. Problems in number theory like Goldbach's conjecture, for example. Maybe we shouldn't think about it in terms of number theory. Finally, we have some references, and thank you for watching my presentation.